The Mathematical Analysis of Logic by George Boole. Of Hypotheticals. A hypothetical proposition is defined to be two or more categoricals united by a copula or conjunction, and the different kinds of hypothetical propositions are named from their respective conjunctions, viz. Conditional, if, disjunctive, either, or, etc. In conditionals, that categorical proposition from which the other results is called the antecedent, that which results from it, the consequent. Of the conditional syllogism there are two, and only two, formulae. First, the constructive. If A is B, then C is D. But A is B, therefore C is D. Second, the destructive. If A is B, then C is D, but C is not D, therefore A is not B. A dilemma is a complex conditional syllogism with several antecedents in the major and a disjunctive minor. If we examine either of the forms of conditional syllogism above given, we shall see that the validity of the argument does not depend upon any considerations which have reference to the terms A, B, C, D, considered as the representatives of individuals or of classes. We may, in fact, represent the propositions A is B, C is D by the arbitrary symbols X and Y respectively, and express our syllogisms in such forms as the following. If X is true, then Y is true, but X is true, therefore Y is true. Thus what we have to consider is not objects and classes of objects, but the truths of propositions, namely, of those elementary propositions which are embodied in the terms of our hypothetical premises. To the symbols X, Y, Z, representative of propositions, we may appropriate the elective symbols lowercase x, y, z in the following sense. The hypothetical universe, 1, shall comprehend all conceivable cases and conjunctures of circumstances. The elective symbol lowercase x, attached to any subject expressive of such cases, shall select those cases in which the proposition uppercase X is true, and similarly for Y and Z. If we confine ourselves to the contemplation of a given proposition X, and hold in abeyance every other consideration, then two cases only are conceivable, viz., first, that the given proposition is true, and secondly, that it is false. Footnote. It was upon the obvious principle that a proposition is either true or false that the Stoics, applying it to assertions respecting future events, endeavored to establish the doctrine of fate. It has been replied to their argument that it involves an abuse of the word true, the precise meaning of which is id quod res est. An assertion respecting the future is neither true nor false. Copleston on Necessity and Predestination, page 36. Were the Stoic axiom, however, presented under the form, it is either certain that a given event will take place, or certain that it will not, the above reply would fail to meet the difficulty. The proper answer would be that no merely verbal definition can settle the question. What is the actual course and constitution of nature when we affirm that it is either certain that an event will take place, or certain that it will not take place? We tacitly assume that the order of events is necessary, that the future is but an evolution of the present, so that the state of things which is completely determines that which shall be. But this, at least as respects the conduct of moral agents, is the very question at issue. Exhibited under its proper form, the Stoic reasoning does not involve an abuse of terms, but a petitio principii. It should be added that enlightened advocates of the doctrine of necessity in the present day, viewing the end as appointed only in and through the means, justly repudiate those practical ill consequences which are the reproach of fatalism. End of footnote. As these cases together make up the universe of the proposition, and as the former is determined by the elective symbol x, the latter is determined by the symbol 1 minus x. But if other considerations are admitted, each of these cases will be resolvable into others, individually less extensive, the number of which will depend upon the number of foreign considerations admitted. Thus, if we associate the propositions x and y, the total number of conceivable cases will be found as exhibited in the following scheme. Case first: x true, y true. Elective expression xy. Case second: x true, y false. Elective expression x open brackets 1 minus y close brackets. Case third: x false, y true. Elective expression open brackets 1 minus x close brackets y. Case fourth: x false, y false. Elective expression open brackets 1 minus x close brackets open brackets 1 minus y close brackets. 24. If we add the elective expressions for the two first of the above cases, the sum is x, which is the elective symbol appropriate to the more general case of uppercase X being true independently of any consideration of y. And if we add the elective expressions in the two last cases together, the result is 1 minus x, which is the elective expression appropriate to the more general case of x being false. Thus the extent of the hypothetical universe does not at all depend upon the number of circumstances which are taken into account, and it is to be noted that however few or many those circumstances may be, the sum of the elective expressions representing every conceivable case will be unity. Thus let us consider the three propositions: x, it rains; y, it hails; z, it freezes. The possible cases are the following. Case first: it rains, hails, and freezes. Elective expression x, y, z. Case second: it rains and hails, but does not freeze. Elective expression x, y, open brackets, 1 minus z, close brackets. Case third: it rains and freezes, but does not hail. Elective expression x, z, open brackets, 1 minus y, close brackets. Case fourth: it freezes and hails, but does not rain. Elective expression yz, open brackets, 1 minus x, close brackets. Case fifth: it rains, but neither hails nor freezes. Elective expression x, open brackets, 1 minus y, close brackets, open brackets, 1 minus z, close brackets. Case 6: it hails, but neither rains nor freezes. Elective expression y, open brackets, 1 minus x, close brackets, open brackets, 1 minus z, close brackets. Case 7: it freezes, but neither hails nor rains. Elective expression z, open brackets, 1 minus x, close brackets, open brackets, 1 minus y, close brackets. Case 8: it neither rains, hails, nor freezes. elective expression, open brackets 1 minus x, close brackets, open brackets 1 minus y, close brackets, open brackets 1 minus z, close brackets, 1 equals sum. Expression of hypothetical propositions. To express that a given proposition x is true, the symbol 1 minus x selects those cases in which the proposition x is false, but if the proposition is true, there are no such cases in its hypothetical universe, therefore 1 minus x equals 0, or x equals 1, 25. To express that a given proposition x is false, the elective symbol x selects all those cases in which the proposition is true, and therefore if the proposition is false, x equals 0, 26. And in every case, having determined the elective expression appropriate to a given proposition, we assert the truth of that proposition by equating the elective expression to unity, and its falsehood by equating the same expression to 0. To express that two propositions x and y are simultaneously true, the elective symbol appropriate to this case is xy, therefore the equation sought is xy equals 1, 27. To express that two propositions x and y are simultaneously false, the condition will obviously be open brackets 1 minus x, close brackets, open brackets 1 minus y, close brackets, equals 1, or x plus y minus xy equals 0, 28. To express that either the proposition x is true or the proposition y is true, to assert that either one or the other of two propositions is true is to assert that it is not true that they are both false. Now the elective expression appropriate to their both being false is open brackets 1 minus x, close brackets, open brackets 1 minus y, close brackets. Therefore the equation required is open brackets 1 minus x, close brackets, open brackets 1 minus y, close brackets, equals 0, or x plus y minus xy equals 1, 29. And by indirect considerations of this kind, may every disjunctive proposition, however numerous its members, be expressed. But the following general rule will usually be preferable. Rule: consider what are those distinct and mutually exclusive cases of which it is implied in the statement of the given proposition that some of them is true, and equate the sum of their elective expressions to unity. This will give the equation of the given proposition. For the sum of the elective expressions for all distinct conceivable cases will be unity. Now all these cases being mutually exclusive, and it being asserted in the given proposition that some one case out of a given set of them is true, it follows that all which are not included in that set are false, and that their elective expressions are severally equal to 0. Hence the sum of the elective expressions for the remaining cases, viz. those included in the given set, will be unity. Some one of those cases will therefore be true, and as they are mutually exclusive, it is impossible that more than one should be true, whence the rule in question. And in the application of this rule it is to be observed that if the cases contemplated in the given disjunctive proposition are not mutually exclusive, they must be resolved into an equivalent series of cases which are mutually exclusive. Thus, if we take the proposition of the preceding example, viz. either x is true or y is true, and assume that the two members of this proposition are not exclusive, insomuch that in the enumeration of possible cases we must reckon that of the propositions x and y being both true, then the mutually exclusive cases which fill up the universe of the proposition with their elective expressions are: first, x true and y false, x open brackets 1 minus y, close brackets. Second, y true and x false, y open brackets 1 minus x close brackets. Third, x true and y true, xy. And the sum of these elective expressions equated to unity gives x plus y minus xy equals 1, 30, as before. But if we suppose the members of the disjunctive proposition to be exclusive, then the only cases to be considered are, first, x true, y false, x open brackets 1 minus y close brackets. Second, y true, x false, y open brackets 1 minus x close brackets. And the sum of these elective expressions equated to 0 gives x minus 2xy plus y equals 1, 31. The subjoined examples will further illustrate this method. To express the proposition either x is not true or y is not true, the members being exclusive, the mutually exclusive cases are, first, x not true, y true, y open brackets 1 minus x close brackets. First, y not true, x true, x open brackets 1 minus y close brackets. And the sum of these equated to unity gives x minus 2xy plus y equals 1, 32, which is the same as 31, and in fact the propositions which they represent are equivalent. To express the proposition either x is not true or y is not true, the members not being exclusive, to the cases contemplated in the last example we must add the following, viz. X not true, y not true, open brackets 1 minus x close brackets, open brackets 1 minus y close brackets. The sum of the elective expressions gives x open brackets 1 minus y plus y open brackets 1 minus x close brackets plus open brackets 1 minus x close brackets open brackets 1 minus y close brackets equals 1, or xy equals 0, 33. To express the disjunctive proposition either x is true or y is true, or z is true, the members being exclusive, here the mutually exclusive cases are, first, x true, y false, z false, x open brackets 1 minus y close brackets, open brackets 1 minus z close brackets. Second, y true, z false, x false, y open brackets 1 minus z close brackets, open brackets 1 minus x close brackets. Third, z true, x false, y false, z open brackets 1 minus x close brackets, open brackets 1 minus y close brackets. And the sum of the elective expressions equated to 1 gives, upon reduction, x plus y plus z minus 2 open brackets xy plus yz plus xz close brackets plus 3 xyz equals 1, 34. The expression of the same proposition when the members are in no sense exclusive will be open brackets 1 minus x close brackets, open brackets 1 minus y close brackets, open brackets 1 minus z close brackets equals 0, 35. And it is easy to see that our method will apply to the expression of any similar proposition whose members are subject to any specified amount and character of exclusion. To express the conditional proposition, if x is true, y is true, here it is implied that all the cases of x being true are cases of y being true, the former cases being determined by the elective symbol x, and the latter by y. We have, in virtue of 4, x open brackets 1 minus y close brackets equals 0, 36. To express the conditional proposition, if x be true, y is not true, the equation is obviously x, y equals 0. 37. This is equivalent to 33. And in fact the disjunctive proposition, either x is not true or y is not true, and the conditional proposition, if x is true, y is not true, are equivalent. To express that if x is not true, y is not true. In 36, write 1 minus x for x, and 1 minus y for y. We have, open brackets, 1 minus x, close brackets, y equals 0. The results which we have obtained admit of verification in many different ways. Let it suffice to take for more particular examination the equation x minus 2xy plus y equals 1, 38, which expresses the conditional proposition, either x is true or y is true, the members being in this case exclusive. First let the proposition x be true, then x equals 1, and substituting we have 1 minus 2y plus y equals 1, therefore negative y equals 0, or y equals 0, which implies that y is not true. Secondly, let x be not true, then x equals 0, and the equation gives y equals 1. 39. Which implies that y is true. In like manner we may proceed with the assumptions that y is true or that y is false. Again, in virtue of the property x squared equals x, y squared equals y, we may write the equation in the form x squared minus 2xy plus y squared equals 1, and extracting the square root, we have x minus y equals plus or minus 1, 40. And this represents the actual case, for as when x is true or false, y is respectively false or true, we have x equals 1 or 0, y equals 0 or 1, therefore x minus y equals 1 or minus 1. There will be no difficulty in the analysis of other cases. Examples of hypothetical syllogism. The treatment of every form of hypothetical syllogism will consist in forming the equations of the premises, and eliminating the symbol or symbols which are found in more than one of them. The result will express the conclusion. First, disjunctive syllogism. Either x is true or y is true exclusive. X plus y minus 2xy equals 1. But x is true, x equals 1. Therefore y is not true, therefore y equals 0. Either x is true or y is true, not exclusive. X plus y minus xy equals 1. But x is not true, x equals 0. Therefore y is true, therefore y equals 1. Second, constructive conditional syllogism. If x is true, y is true. X, open brackets, 1 minus y, close brackets, equals 0. But x is true, x equals 1. Therefore y is true, therefore 1 minus y equals 0, or y equals 1. Third, destructive conditional syllogism. If x is true, y is true. X, open brackets, 1 minus y equals 0. But y is not true. Y equals 0, therefore x is not true, therefore x equals 0. Fourth, simple constructive dilemma, the minor premise exclusive. If x is true, y is true. X, open brackets, 1 minus y, close brackets, equals 0, 41. If z is true, y is true. Z, open brackets, 1 minus y, close brackets, equals 0, 41. But either x is true or z is true. X plus z minus 2xz equals 1, 43. From the equations 41, 42, 43, we have to eliminate x and z. In whatever way we effect this, the result is y equals 1, whence it appears that the proposition y is true. Fifth,
Complex constructive dilemma, the minor premise not exclusive. If x is true, y is true. X, open brackets, 1 minus y, close brackets, equals 0. If w is true, z is true. W, open brackets, 1 minus z, close brackets, equals 0. Either x is true or w is true. X plus w minus xw equals 1. From these equations eliminating x, we have y plus z minus yz equals 1, which expresses the conclusion either y is true or z is true, the members being non-exclusive. Sixth, complex destructive dilemma, the minor premise exclusive. If x is true, y is true. X, open brackets, 1 minus y, close brackets, equals 0. If w is true, z is true. W, open brackets, 1 minus z, close brackets, equals 0. Either y is not true or z is not true. Y plus z minus 2yz equals 1. From these equations we must eliminate y and z. The result is xw equals 0, which expresses the conclusion either x is not true or y is not true, the members not being exclusive. Seventh, complex destructive dilemma, the minor premise not exclusive. If x is true, y is true. X, open brackets, 1 minus y, close brackets, equals 0. If w is true, z is true. W, open brackets, 1 minus z, close brackets, equals 0. Either y is not true or z is not true. Yz equals 0. On elimination of y and z, we have xw equals 0, which indicates the same conclusion as the previous example. It appears from these and similar cases that whether the members of the minor premise of a dilemma are exclusive or not, the members of the disjunctive conclusion are never exclusive. This fact has perhaps escaped the notice of logicians. The above are the principal forms of hypothetical syllogism which logicians have recognized. It would be easy, however, to extend the list, especially by the blending of the disjunctive and the conditional character in the same proposition, of which the following is an example. If x is true, then either y is true or z is true. X, open brackets, 1 minus y minus z plus yz, close brackets, equals 0. But y is not true. Y equals 0. Therefore, if x is true, z is true. Therefore, x, open brackets, 1 minus z, close brackets, equals 0. That which logicians term a causal proposition is properly a conditional syllogism, the major premise of which is suppressed. The assertion that the proposition x is true because the proposition y is true is equivalent to the assertion the proposition y is true, therefore the proposition x is true, and these are the minor premise and conclusion of the conditional syllogism: if y is true, x is true, but y is true, therefore x is true. And thus causal propositions are seen to be included in the applications of our general method. Note that there is a family of disjunctive and conditional propositions which do not, of right, belong to the class considered in this chapter. Such are those in which the force of the disjunctive or conditional particle is expended upon the predicate of the proposition, as if, speaking of the inhabitants of a particular island, we should say that they are all either Europeans or Asiatics, meaning that it is true of each individual that he is either a European or an Asiatic. If we appropriate the elective symbol x to the inhabitants, y to the Europeans, and z to the Asiatics, then the equation of the above proposition is x equals xy plus zx, or x, open brackets, 1 minus y minus z equals 0, a. to which we might add the condition yz equals 0, since no Europeans are Asiatics. The nature of the symbols x, y, z indicates that the proposition belongs to those which we have before designated as categorical. Very different from the above is the proposition, either all the inhabitants are Europeans or they are all Asiatics. Here the disjunctive particle separates propositions. The cases that contemplated in 31 of the present chapter, and the symbols by which it is expressed, although subject to the same laws as those of A, have a totally different interpretation. Footnote. Some writers, among whom is Dr. Latham, first outlines, regard it as the exclusive office for conjunction to connect propositions, not words. In this view I am not able to agree. The proposition, every animal is either rational or irrational, cannot be resolved into either every animal is rational or every animal is irrational. The former belongs to pure categoricals, the latter to hypotheticals. In singular propositions, such conversions would seem to be allowable. This animal is either rational or irrational is equivalent to either this animal is rational or it is irrational. The peculiarity of singular propositions would almost justify our ranking them, though truly universals, in a separate class, as James Spencer did. End of footnote. The distinction is real and important. Every proposition which language can express may be represented by elective symbols, and the laws of combination of those symbols are in all cases the same. But in one class of instances, symbols have reference to collections of objects, and the other to the truths of constituent propositions.